Hey guys, what's up? In this video, we're going to talk about the cake eating problem over a infinite time horizon. Let's go. So the setup is similar to our finite horizon model, which we discussed in our previous video. There is a fixed cake. Our consumer is deciding how to consume over a infinite horizon though. In this case, we're interested in identifying time invariant policy functions which do exist in this case. So in terms of setting up the problem, suppose you are someone deciding how to consume a cake over an infinite period of time where t goes from period 1 to period 2 all the way out to infinity. This is the discrete case, obviously. In this case, we will be considering the instantaneous preferences denoted by the natural log of ct, which is the consumption at time t. In general, the sequential problem for the cake eating problem in, I guess, an infinite time horizon could be written as the following. Just note that instead of having a capital T at the top, we have infinity, right? So because it goes out forever. The corresponding functional equation from this, from our principle of optimality is the following, right? Which is this maximization problem with respect to the cake size in the next period. What we're interested in from this problem is finding the time invariant policy functions for both this cake size in the next period, which is sometimes interpreted as the investment or the saving of leftover. I shouldn't say savings rate, but it's the amount that should be saved for the next period and the consumption. So the way we're going to solve this problem is going to involve 6 steps, and we're going to go through each one of these. Step 1 is that we're going to set up the Bellman equation. Step 2 is that we're going to take a guess for what Vt is and use that in our Bellman, meaning that for the Vt plus 1 part in our functional equation, right, we're going to plug in what our guess is going to be. In step 3, we're going to take our first order conditions and solve for this xt plus 1 tilde, meaning the cake size in time t plus 1, right? Though this is an intermediate step. And from there, we're going to take our initial guess and set it equal to our value equation evaluated at this xt plus 1 tilde. In step 5, we're going to go then identify the coefficients from our guess because for our guess to be, I guess, have some meaning to it, we have to go and ascribe what exactly the parameters are for our guess, because there'll be real values attached to them, as in we're not throwing in arbitrary numbers. And step 6 is that we're going to use the coefficients, right, once we solve for them, to identify our policy functions from x tilde t plus 1. So let's work through each one of these steps. So step 1, set up the Bellman equation. So as you see, this is just the functional equation that we had before. Step 2, we're going to take a guess for what Vxt is, right? So in this case, we're just going to go and take this equation as it's just like a linear equation, right? It's C1 plus C2 times ln xt, right? So that's the form of our Bellman equation. So notice here that we're taking a guess that is very similar to the structure of our preferences before. So that's just really a general rule for choosing an appropriate guess, but I'll talk about that a little bit more probably in another video. And if we were to sub that into our Bellman equation, we get the following result. Moving on to step number 3, we take our first order condition and solve for xt plus 1 tilde, which will be our intermediate value. As we could see, we took our first order condition over there and rearranged this, and we got this guy right in the middle that I have boxed in. Step 4, we're going to take our initial guess and set it equal to our Bellman equation evaluated at this xt plus 1 tilde. So I'm going to do a little bit more of this simplifying on the next slide. Further simplifying, we go and we get the following result. So I have some algebra over here, but I just want to point out these 2 points, 1 and point 2. We can see that our constant term C1 must be equal to the constant term on our right-hand side in order for this equality to be true. So C1 is going to be equal to 1. And we require that our coefficient on ln xt needs to be equivalent on both sides. So this implies that we have C2 is equal to 1 plus beta C2, or C2 star is equal to 1 over 1 minus beta. So we have an actual value for our coefficient C2, which is specifically important for deriving our policy function. So in our sixth and final step, right, we just go and we sub in what our values will be for C2, right? And our policy function is usually denoted by g of xt. And after doing a little bit of algebra, we go and we find that our policy functions is equal to beta times xt, meaning that we should go and save that proportion, or that proportion should be left over for the next period forever. And the corresponding consumption policy function is denoted by the following, which is xt times 1 minus beta. So that's solving the cake eating problem over infinite time. I hope this video helps. Let me know in the comments below. Take care.